small block along the common normal is b, and this should be equal to the acceleration of triangular wedge along the common normal. So suppose this angle is alpha, so this is 90 degrees, so this will be 90 minus alpha, so b must be equal to a cos 90 minus alpha, that is a sin alpha. So this is the equation of motion we get using the contact constraint. Now we will start the chapter dynamics of circular motion. So when an object moves in a circle, direction of its velocity vector changes continuously. So suppose there is an object which is moving around a circle. Suppose at time t is equal to t1, the object is at point A. So the velocity vector of this object will be like this. Let's say after some time, that is at t is equal to t2, object moves to point B, and here the velocity vector will look like this. So the velocity vector is always tangent to the circle. So you can see from here that the direction of velocity vector has changed. At point A it is in this direction, that is horizontal direction, and at point B its direction has changed. So even though the magnitude of velocity remains same, its direction has changed, so which means that velocity vector has changed. Since there is a change in velocity, there must be some acceleration which is acting on the object. This acceleration is responsible for the change in the direction of velocity vector, and it is called centripetal acceleration. The value of centripetal acceleration is v square by r, where v is the magnitude of the velocity and r is the radius of circle, and the direction of this acceleration is always towards the center of the circle. So taking the same example, we have an object which is on a circular path, which is moving on a circular path. So at point A its velocity is in this direction, and at point B its velocity in this direction. Now the centripetal acceleration acting on the object is always directed towards the center, that is, this is the direction of centripetal acceleration at point A, and at point B the direction is this. So this is the direction of centripetal acceleration, this is the direction of velocity. Now magnitude of centripetal acceleration is v square by r, where v is the magnitude of velocity vector and r is the radius of the circle. Since an object which is in circular motion is always accelerated, there must be some force which is responsible to generate this acceleration. This force is called centripetal force, and the direction of this force is always towards the center of the circle, and the magnitude of this force is mv square by r. So taking the same example again, if we have an object which is moving around a circle, then there will always be a force acting on it. This is its direction is towards the center, so this is the force acting on the object at point A. At point B, this is the force acting on the object. This force is called centripetal force, and its value is mass times centripetal acceleration, that is v square by r. where m is the mass of the object, v is the magnitude of its velocity, and r is the radius of circle. Now let's define centrifugal force. Suppose there is an object which is being viewed from a frame of reference which is rotating about an arbitrary axis with angular velocity omega. Due to non-inertiality of this frame of reference, the object appears to be experiencing a pseudo force which is radially outwards from the axis of rotation, and the magnitude of this force is mv square by r. This force is called centrifugal force. So suppose there is an object of mass m and there is an observer which is moving around a circle. This is the axis of rotation of the circle. The angular velocity of the rotation is omega. The radius of circle is r, so the linear velocity v would be omega r. Now for this observer, this stationary object will not appear to be at rest. Instead this observer will find that there is a force, a pseudo force, which is acting on this object. The magnitude of this pseudo force is mv square by r, where m is the mass of the object. Now this is a force which we call centrifugal force. So suppose the observer is at this point. So observer is experiencing a centripetal force in this direction towards the center. So for this observer, this object will appear to be experiencing a force which is directly opposite to the centripetal force in the radially outward direction. Similarly, if the observer is at this point, he will experience a centripetal force towards the center. Now for observer, the object will appear to be experiencing a force in this direction which is directly opposite to the direction of centripetal force. So this happens because the frame of reference where the observer is, it's a non-inertial frame of reference. Because this frame of reference is always accelerated, there is a centripetal acceleration which is being acted upon the observer. So for observer, a stationary object will not appear to be at rest, and the observer will find that the object is being acted upon by a centrifugal force of the magnitude mv square by r. Now we'll see some real life example involving circular motion. We'll take the example of an object which is moving in a rough plane track, an object which is moving in a smooth blank track, and an object which is moving in a rough blank track. So let's first see the rough plane track example. So here this is our example of rough plane track, that is the track is not banked, and this is the example of smooth plane track. So suppose there is an object which is moving in a circular path, and the track on which it is moving is rough and it is plane track, that is the track is not banked. So suppose the object is at some point A. This is our object. So at any given point the forces acting on the objects are its weight mg, the normal reaction from the track, and the friction force since the track is rough. So the friction force is the force